So here in 8.6, we are solving exponential equations. So equations meaning we have an equal sign, exponential meaning that my variable x is in the exponent, all right? So we're gonna be solving these, meaning that our final answer should look like x equals a number. That should be our final answer. I always wanna start by isolating the powers if possible. So remember, the power is like b to the x power. We have a base, we have an exponent. So if I look at this first example here, I can see that my power is not isolated on the left side. There's still a 2 over here. And I cannot multiply the 2 and the 8 together because that would be breaking order of operations, right? If I think about PEMDAS, please excuse my dear Aunt Sally, we know that exponents, right, this part here has to come before multiplication, which is that there. So you could not change this into a 16, that would be incorrect. Instead, we have to get rid of that 2, so I could divide both sides by 2, and that would give me 8 to the x plus 2 power equals 5. And so you can see I've now got this isolated, and so the power is isolated. I could then go to the next step of the problem. All right? This is not your final answer, but that is how you would then begin the rest of the work. For the second one here, we could take 4 and subtract it on both sides, again trying to get this power all by itself. So that would then give me, 1/2 times 3 to the x minus 7 equals 14. I then want to get rid of the 1/2 so I can multiply both sides by 2. 1/2 of 2 is just 1, so those cancel. And 3 to the x minus 7 equals 28. So again, this is not your answer, but this is how you would begin the next step of the problem solving. And then this last one here. Now notice this one we have 2 powers, right? I have 2 to the 2x plus 1 and 16 to the x minus 3. So we might think to ourselves, oh, well, if I just divide both sides by 4, but then, yeah, it cancels on the right, but now I have a 4 in the denominator. So in this case, it's not really helpful to divide by 4 because we still have a power on each side. In this case, it's going to be most beneficial to us to rewrite the 4 as 2 squared. So if we change everything into a power, that would be 2 to the 2x plus 1 equals 2 squared. We know 16 is the same as 2 to the, not 2 to the 8th, 2 to the 4th power. And then we still have that x minus 3. So this should look familiar to you. We did this in chapter 8.2 where we tried to get all the common base. And that's actually going to be our first method here. All right, method 1 is to try to get each power using the same base. All right, so for a problem like this, we are able to get the same base of 2 for every single piece. However, if that doesn't work, right, this is your first method to try this. If it doesn't work getting the same base, that means that you're going to take the logarithm of both sides. So method 2 would be something that we might want to use for this example here, because there's no way to get 3 and 28 to have the same base. It could also work here because there's no way to get 8 and 5 to have the same base, right? So we had to take the logarithm of both sides. Again, in mathematics, we know that whatever we're allowed to do on one side, we can do the same thing on the other side as well. So the ways that you could take the logarithm of both sides, you could use the common logarithm, which is just log. Remember, the base is 10 there, even though we don't write the 10. We could use the natural logarithm, which is ln. And we could use any other logarithm, like log base 2, or log base 3, or log base 4. But if you do it this way, you just kind of want to be intentional, all right? And what I mean by that is that you have to pick certain numbers that are going to make your life a little bit easier for you, all right? So let's get into problem number 1, and let's try to solve this. So first thing, I see this power, and I realize it's not isolated. So I'm going to try to isolate this. So we're going to go ahead and let's subtract 5 on both sides. That's going to give me 3 times 4 to the 2x minus 1 equals 24. I then need to isolate my power still, so we're going to divide by 3. And now we know that 4 to the 2x minus 1 equals 8. All right, so now the question is, which method do I use? Well, I could try to write each power using the same base, and that is a method that actually works out well for me in this problem. All right, I can rewrite the 4 as 2 squared. I still have the 2x minus 1, and I can rewrite the 8 as 2 cubed. All right, so now I can see that I have the same base of 2. We can do a little distributing, so 2 to the 4x minus 2 equals 2 to the 3rd. I just distributed this 2 to both parts. And now because I have the same base, I'm allowed to say that the exponents are equal. So 4x minus 2 equals 3. We're going to go ahead and we're going to add 2 on both sides. And we see that 4x equals 5. And then if we divide both sides by 4, we just get x equals 5/4. Okay? Whenever you do problems where you get the same base, you are going to get nice numbers. What I mean by nice numbers, they could be natural numbers. They could be integers, bright positives, negatives. They could be fractions, 2/3, 1/5. Whenever you use method number 2, you are going to have to use your calculator, all right? Now, I say that because we're assuming that if we can't use method number 1, we're going to go with method number 2. But typically when you're doing method number 2, you're going to want to use your calculator for that one, all right? So these are going to be on the calculator section. Method number 1 is going to be on a non-calculator section. So let's look at number 2 here. So in question number 2, again, I see that my base with the exponent is not isolated, so I'm going to try to get that isolated first by adding 11 on both sides. And we have 5 to the x plus 2 power equals 27. So at this point here, my power is isolated. So I'm going to try to think about, do I want to do step 1? Well, method 1, I'm trying to get the same base. But there's no way I could get a same base with the number 27, right? It's 3 to the 3rd power, but 3 and 5 are different numbers. So I can't get the same base using method 1, which means I'm going to use method number 2. Now in method number 2, again, like I said, you could use whatever kind of logarithm you want. So I'm going to show you how to do this 3 different ways. The first way, we're going to take the common log of both sides. So we're going to say log of 5 to the x plus 2 power equals the log of 27. All right, that's one way to do it. Another way to do it is using the natural log. So you can say that the natural log of the left side, x plus 2, equals the natural log of the right side. All right, and then the last way to do it is kind of that way that you have to be a little bit thoughtful. All right, so what I mean by thoughtful is you want to pick a base that's the same as either of these bases, all right? So I typically like to, one of my preferences is to use the same base as the base of whatever my power is. So I'm going to choose log base 5 for this one. All right, let's see what happens there. So I'm going to do log base 5 of 5 to the x plus 2 equals log base 5 of 27. All right? So those are 3 different ways that we could do this, and let's try to solve each of these. You're going to notice some similarities here, especially within the first 2. So first thing I'm going to do is I'm going to use my power property of logarithms, right? We learned this in the 8.5 notes that you just watched, and the power property says if I have an exponent here, I'm allowed to bring that out in front and multiply it by the logarithm. So this is really the same thing as x plus 2 times the logarithm of 5. And that's going to equal the logarithm of 27. All right, same thing with the natural log. We can do that same rule, right? The rule is I can take the exponent, bring it out in front, and that's going to give me x plus 2 times the natural log of 5 equals the natural log of 27. And then lastly, we can do the same exact process here where we bring that out front, and I'm going to get x plus 2 times the log base 5 of 5 equals log base 5 of 27, okay? Again, those orange steps, if you're confused why I'm doing that orange step and how I'm allowed to do that, you need to go back to the 8.5 notes that you just watched and rewatch those a little bit more carefully. This is one of our rules. It's called the power property of logarithms. So make sure you watch it a little bit more carefully to know that we're allowed to do this. This is going to come up a lot, so you need to make sure you know this rule. At this point here, we're going to go back to this problem, and I want to get the x all by itself. So to do that, I'm going to have to divide both sides by the log of 5. Divide by log of 5. These will cancel on the left, leaving me with x plus 2 equals the log of 27 divided by the log of 5. Now I can do the same exact thing in the middle step. The natural log of 5 is being divided on both sides. Cancel, cancel. And we've got x plus 2 equals ln of 27 divided by ln of 5. And then the last one, same idea, but a little bit different here is that we know that log base 5 of 5 is really just equal to 1, right? We're asking ourselves 5 to what power equals 5? Well, 5 to the first power is just 5. So the nice thing about this, by being intentional, is that anything, right, this x plus 2 times the 1 is just x plus 2. So really what I have here is x plus 2 equals log base 5 of 27. All right, so a little bit less going on in that last one. Notice how it's a little bit nicer for me. Last thing I have to do is I just have to move this 2 over to the right side. So what I'm going to go ahead and do is I'm going to subtract 2 on both sides. And that's going to give me x equals log of 27 divided by log of 5 minus 2. Over here, we're going to do the same thing, subtract 2 on both sides. That's going to give me x equals the natural log of 27 divided by the natural log of 5 minus 2. And then lastly, same idea, we're going to go ahead and we're going to subtract 2 on both sides. And so we get x equals log base 5 of 27 minus 2. All right, remember, make sure this 2 comes at the very end. It's not part of a parenthesis, so it's not like 27 minus 2 and then take the logarithm. You take the logarithm base 5 of 27 and then subtract 2. Now at this point here, these values that I've got in red are decimals. They are irrational numbers. You must use your calculator to evaluate them, okay? You can probably, if you're thinking ahead, you can probably see that if I use my change of base formula, this is the same as either of these. That's kind of where this comes from, why we know this is true. So at this point here, you're going to go on your calculator, and you're going to type in exactly what you see here, and here, and here, and it's not going to matter. You are going to get the exact same answer either way. So if I were to go on my calculator and actually type this out, we'd get a value for all three of them. That would be about 0.04781858, and it keeps going on, okay? I'm going to ask you to round to the nearest, let's say, hundredth. So we're going to say that x is about 0.05, okay? But the nice thing about this, again, is you get to choose. If you want to use the common logarithm, great. If you want to use the natural logarithm, great. If you want to use log base 5, right? 5 because it matches up with the base of 5, great, all right? Either way, you will get the correct answer, so you don't have to worry. It's really just up to personal preference, whichever method you choose to use, all right? I kind of like this one because it's a little bit less work, and I kind of like that cleverness that you can apply. Problem 3. Here we have 7 to the x squared equals, well, notice I've got 2 powers. So if I have 2 powers, one on either side, this is kind of like the very beginning example we did here in the green, right? There's no way I can get both powers all by themselves. So I'm going to try to change this 1/7 into a power as well, right? I'm going to try to get common bases of 7. So I know that 1/7 is really 7 to the negative first power times, well, we know that 49 is 7 squared to the x plus 2 power. All right, so I just changed the 49 into 7 squared. I changed 1/7 into 7 to the negative first, all right? But now I have all common bases, right? They're all 7s. So now, because they're all 7s, I can say that x squared equals -1 plus, remember the rule is when I multiply powers, I have to add the exponents. So -1 plus 2x plus 4. Well, where'd this 2x plus 4 come from? That's just distributing this 2 to both these pieces. All right, that's where that comes from. We did this in 8.2, so this is just a review of 8.2. So now I've got x squared equals 2x plus 3. Well, if I have a quadratic, I want to set it equal to 0 and solve. So x squared minus 2x minus 3 equals 0. I'm looking for two numbers that multiply to be -3, but add up to equal -2, and that's got to be a -3 and a +1. And so that gives me x minus 3, x plus 1 equals 0. So we know that our answers have to be +3 and -1. And there you go. Again, we chose to do method number 1 where we get the same base. So you can see that my numbers worked out to be kind of nicer numbers, right? They're not irrational numbers that I had to use my calculator for. This is a non-calculator problem. All right, question number 4. I see this is my power, so I'm going to try to isolate this. That means I'm going to have to try to multiply both sides by 4 to get rid of that 1/4, all right? 4 times 1/4 is just 1, So the 1 will cancel. 6 to the 3x plus 1 equals 12. So the question is, can I get the same base? And the answer is no, right? I can't do like 2 to some power equals 6 or 3 to some power equals 6. I know that 6 to the first power is 6, but then 6 to what power would be 12, right? It's not going to work. So there's no way we can get common bases. That means I'm going to try to take the logarithm of both sides, all right? So I'm going to do, we haven't really done a lot with natural logarithms, so I'm going to do natural logarithms here, all right? But again, you can choose common logarithms, or you could even do log base 6 if you want, all right? You could do log base 6 on both sides if you prefer. So I'm going to do the natural logarithm. So I'm going to take the natural logarithm of the left, so ln of 6 to the 3x plus 1 equals ln of 12. All right, now I have to use my power property, so we know this exponent can come out in front and get multiplied. So now I have a 3x plus 1 times the ln of 6 equals the ln of 12. All right, I now want to get this x all by itself, and I can see that's being multiplied by the ln of 6. So to undo that multiplication, we have to use division. So I'm going to divide both sides by the ln of 6. Ln of 6 cancel. And now I can see that we've got 3x plus 1 equals ln of 12 divided by ln of 6. One common mistake that I see all the time is people like to say that the ln of 12 divided by the ln of 6 equals the ln of 2. This is incorrect. That is not true. You cannot do that, so don't even think about it. That's not how this works. All right, you can't just divide the 12 and the 6 and get 2. All right, that's not how we do this. So you have to leave it like this. Don't go on your calculator just yet, because once you round a number and then use that to multiply or divide or anything else, your number is going to get further and further off from that approximation that you have. So don't put it on your calculator just yet. We're going to get everything away from the x first. So I'm going to go ahead and subtract 1 on both sides. So now we have 3x equals ln of 12 divided by the ln of 6, and then we're subtracting 1. Last thing I have to do is divide by 3, so we're going to divide all of this by 3. So that means I have x equals the ln of 12 divided by the ln of 6 minus 1, and then all of that is divided by 3. So if you're wondering how to do this on your calculator, my advice would be to first type in ln of 12, and you can divide that by the ln of 6. All right, that should give you about 1.38 repeating. All right, but now what you're going to do is you're going to just subtract 1 from that. So hit the minus 1, hit enter, and then all of that numerator, which is about 0.386 or so, you're now going to divide all of that by 3 and hit enter. And this should be approximately, we're going to round to the nearest, let's do thousandths. So let's do 3 decimal places, about 0.129. All right, so you should get this value here. So again, what this means is if I plug in a 0.129 for x, all right, for this x value right here, we should get a true statement. All right, I'm not expecting you to do that because this is an irrational number. This would be really hard to plug in and figure it out, but that's how we would approach these. All right, so to recap, the main idea here is that once you get the power isolated, right, get the power all by itself. Once you've done that, you can try to rewrite each power using the same base. That's your first method. If that doesn't work, then you're going to take the log of both sides, okay? When you take the log of both sides, you get your choice of common, natural, or choosing a base that's going to be most convenient to you, right? From there, it's just a matter of simplifying. And then if you do have to use method number 2 here, this is going to be a calculator problem, all right? So if I do ask you to do that, a problem like that where you have to use the logarithms, then you're going to have to use your calculator for that. So make sure you know how to use your calculator as well.